Welcome, take a slow, gentle breath in and let it out. Tonight, you don't need to think, you don't need to worry, and you don't need to rush. Just allow yourself to sink into this moment. Let your body relax, your mind soften, and your thoughts slowly drift away. As you listen, imagine yourself floating into a peaceful, quiet space, where every word guides you deeper into calm, deeper into comfort, and eventually into a deep, restful sleep. Now just listen. There is a place beneath the ice where the rules of exploration break down entirely. Not because of danger alone, though danger is omnipresent, but because the environment itself seems architected to resist discovery. Beneath the glaciers of the Arctic, underneath hundreds of meters of shifting, grinding ice that has accumulated over hundreds of thousands of years, lies a world that modern science can barely see, let alone enter. It is not the ocean floor of the tropics, teeming with coral and light-filtered life, cataloged by satellites and mapped by fleets of autonomous vehicles. It is something far stranger, something that actively hides. In the summer of 2018, a team of international scientists attempted to thread an instrument package beneath the Thwaites Glacier in Antarctica using a borehole drilled by a jet of hot water. The borehole was roughly 35 centimeters in diameter, barely wider than a dinner plate. The glacier above was 600 meters thick. The process took weeks. By the time the instruments descended into the subglacial ocean below, scientists had perhaps 24 hours before the hole began to refreeze and swallow the equipment entirely. What they found in those hours upended assumptions that had been standing for decades. The water wasn't supposed to be warm. The currents weren't supposed to be moving that fast. And the sediment on the bottom showed signs of disruption that suggested something had been happening down there for years. Silently, invisibly, with no human witness. That is the central paradox of subglacial exploration. We live in an age of extraordinary technological reach. We have sent rovers to Mars. We have imaged black holes 55 million light-years away. We have mapped the floors of the world's deepest ocean trenches with millimeter-scale precision. And yet the space directly beneath the Arctic's glaciers, a realm measured not in light years but in hundreds of meters, remains one of the most profoundly inaccessible environments on Earth. The ice itself is the barrier, not just physically but logistically, scientifically, financially, and in ways that border on the philosophical. To understand why, you have to understand what that ice actually is. The glaciers sitting atop the Arctic are not static. They are rivers in the slowest sense imaginable, masses of compressed snow and ice that flow, fracture, surge, and calve over timescales that stretch from decades to millennia. At their base, where ice meets rock or sediment, temperatures and pressures conspire to create pockets of liquid water. These subglacial lakes, some of them the size of small seas, sit in darkness that has never been broken by sunlight. Some have been isolated for millions of years. They are not frozen wastelands. They are ecosystems. And reaching them requires threading the eye of a needle in a system that is constantly, imperceptibly moving. The challenge is not merely one of drilling. Any engineer will tell you that drilling through ice is solvable. Hot water, pressure, mechanical cutters, all viable. The challenge is what you do once you're through. The borehole begins closing the moment it's created. The instruments you lower must be small enough to fit, robust enough to withstand pressures that approach those found at significant ocean depths, sterile enough not to contaminate an ecosystem that has evolved in perfect isolation, and smart enough to transmit data before the window closes. Every variable fights you. Every minute counts. And if the glacier surges, as they occasionally do, moving meters in hours rather than the usual centimeters per day, your equipment, and potentially your team, faces consequences that no amount of planning can fully anticipate. This is the story of why we can't truly explore beneath the North Pole's glaciers. Not for lack of courage, or curiosity, or funding alone, but because the ice has built defenses that operate on geological timescales, while human ambition operates in grant cycles of 3 to 5 years. It is the story of what we suspect lives down there. What we know is happening down there that will affect every coastline on the planet, and what it would actually take, technologically, politically, and physically, to finally see it. The first mistake most people make when imagining Arctic glaciers is to think of them as solid, permanent, inert. The word glacier carries a sense of geological patience that borders on stillness, the kind of thing that changes only when you compare photographs separ, aided by decades. But this is a dangerous misunderstanding, and it is one that has nearly killed explorers, destroyed equipment worth millions of dollars, and fundamentally complicated every attempt to study what lies beneath. A glacier is a crystal. At the molecular level, ice behaves according to rules that differ profoundly from the rock and soil that humans typically drill through. Ice deforms plastically under sustained pressure, meaning it doesn't simply crack and stay cracked. It flows around obstacles, seals openings, and redistributes stress in ways that make conventional borehole engineering nearly useless without constant intervention. Drill a 30-centimeter hole through 500 meters of ice, and within hours, the ice at depth will begin creeping inward. Within days, the hole is gone. The glacier has healed itself, as if the intrusion never happened. This behavior arises from a property called creep deformation. At temperatures near the melting point, which is precisely where the base of most Arctic glaciers sits, ice grains slide past one another along their crystalline boundaries. The entire mass flows, not in the way water flows, rushing and turbulent, but in the way a crowd of people flows, each element moving incrementally, the whole system nonetheless traveling measurable distances. The Greenland ice sheet, the largest glacial body in the northern hemisphere, moves at rates between 20 and 40 meters per year in some of its outlet glaciers. That might sound slow, but for an instrument package tethered by a cable and lowered into a closing borehole, even centimeters per hour is enough to shear connections, snap tethers, and entomb equipment permanently. Glaciologists measure this movement with GPS arrays drilled into the ice surface, tracking positions to millimeter accuracy. What those arrays reveal is not the smooth, steady creep of intuition, but something altogether more alarming: a pulsed, episodic flow punctuated by events called surge cycles. A surging glacier can accelerate by factors of 10 or more over periods of weeks to months, then slow back to its baseline. The Vavilov ice cap in the Russian Arctic surged beginning in 2013 at speeds reaching 25 meters per day, roughly 1,000 times faster than its previous rate. Equipment on or in a surging glacier doesn't simply get damaged. It gets transported. And when the surge ends and the ice settles back, what remains is compressed, deformed, and utterly inaccessible. Understanding why glaciers surge has been one of glaciology's persistent puzzles, and the answer, insofar as science has converged on one, lies precisely in the subglacial environment that explorers are trying to reach. The base of a glacier sits at the pressure melting point, which means the enormous weight of the ice above lowers the freezing temperature of water just enough to maintain a thin film of liquid between ice and bedrock. This basal meltwater lubricates the interface. When it accumulates faster than it can drain, pressure builds, and the frictional resistance that normally anchors the glacier to its bed decreases. The glacier, suddenly freed, lurches forward. It is a hydraulic release valve, and the trigger is the very water that scientists most want to study. This creates a feedback loop that makes subglacial research simultaneously urgent and treacherous. The meltwater at the base of Arctic glaciers is not merely a curiosity. It is the mechanism by which glaciers connect to the ocean, by which warming signals from Atlantic and Pacific water masses are transmitted through hundreds of meters of ice to affect flow rates, calving dynamics, and ultimately sea level. The water that scientists are trying to reach is the same water that is actively destabilizing the ice above. Every attempt to study the system disturbs it in ways that are difficult to quantify. And the system, when disturbed, has a way of responding with force. The North Pole region adds additional complication because of the nature of the sea ice that covers the Arctic Ocean itself. Unlike the land-based glaciers of Greenland or the Antarctic Peninsula, the ice directly over the North Pole floats. It is sea ice, frozen ocean water that forms, drifts, fractures, and refreezes over seasonal and multi-year cycles. The oldest Arctic sea ice, designated multi-year ice, can reach thicknesses of 4 to 5 meters. But it is in constant motion, driven by wind and ocean currents, and it fractures unpredictably. Scientists attempting to work on the ice surface, drilling downward through sea ice into the Arctic Ocean below, are working on a platform that can split beneath their feet without warning, opening leads of open water meters wide in minutes. Several research stations have been abandoned in the face of exactly this threat. One, the Soviet-era North Pole 1 station established in 1937, drifted more than 2,500 kilometers over 9 months before the ice platform it sat on began breaking up. The scientists were extracted by aircraft. The station was not. The Polarstern, the German icebreaker that served as the drifting research platform for the Mosaic expedition from 2019 to 2020, spent 389 days locked in Arctic sea ice, drifting with it for 3,400 kilometers across the central Arctic. The scientists aboard studied the ice and the ocean beneath from a vessel that was itself subject to the same forces they were studying. On multiple occasions, Ice dynamics forced the abandonment of instrumentation laid on the ice surface. Pressure ridges, formed when ice flows collide and buckle upward into walls of compressed ice that can reach 4 meters in height, formed near the ship's hull with speeds that left no time for deliberate response. The crew moved quickly, and the ridges formed where they had been standing. The Arctic ice does not negotiate. And yet this is the crucial point. All of this describes the surface. What lies beneath, in the dark space between ice base and ocean floor or bedrock, is a realm that makes the surface look positively accessible. The pressures at depth prevent casual instrumentation. The closure of boreholes limits access time. The contamination risk to pristine ecosystems restricts what equipment can be introduced. And the sheer scale of the subglacial environment. The Arctic Ocean alone covers 14 million square kilometers, much of it overlaid by sea ice for significant portions of the year, means that even heroic point measurements at single locations leave the vast majority of the system utterly uncharacterized. Scientists have a name for this. They call it the data desert, not because nothing is there, but because everything that is there refuses to be seen. 600 meters of ice weighs approximately 540,000 kilograms per square meter. If you convert that to pressure, the kind of pressure that acts on every surface of every instrument lowered into the space beneath, you arrive at roughly 53 atmospheres. That is more than 5 times the pressure at the surface of the ocean, and comparable to the pressure experienced at 530 meters below the sea surface. It is enough to crush a standard pressure housing designed for recreational diving. It is enough to implode a poorly sealed connection in microseconds. It is enough, in short, to make engineering a genuine adversary rather than a mere constraint. The engineering challenge of building instruments for subglacial exploration is therefore not trivially solvable by borrowing technology from oceanography, though oceanographers have spent decades building instruments for high-pressure environments. The difference is not merely in the magnitude of pressure, but in the geometry of access. An oceanographic instrument deployed from a research vessel descends through open water, steered by thrusters, tracked by acoustic transponders, and recoverable by releasing a ballast weight that allows it to ascend on its own buoyancy. The ocean is, in this sense, a cooperative medium. It holds instruments in suspension, allows them to move freely, and returns them when commanded. Beneath a glacier, none of this applies. The instrument enters through a borehole perhaps 30 to 40 centimeters in diameter, a constraint that imposes brutal limitations on the size of anything that can be sent down. It descends through a tube of water maintained by the drilling operation itself, water that begins refreezing the moment the hot water drill is withdrawn. It cannot maneuver freely because it is physically constrained by the borehole walls. And it cannot ascend by buoyancy alone because there is no open water column, only a narrow cylinder of ice that is actively trying to close around it. The instruments developed for subglacial access therefore represent some of the most precisely engineered scientific tools ever built. The IceCube Neutrino Observatory in Antarctica, which uses hot water drilling to deploy particle detectors deep in the ice sheet, provides a useful comparison. IceCube's boreholes reach 2,500 meters and are drilled by a specialized hot water drill system that requires 5 million watts of thermal power and 760,000 liters of water recirculated through heaters. The boreholes are approximately 60 centimeters in diameter, and each one must be drilled, instrumented, and sealed within roughly 48 hours before refreezing eliminates access. The detectors lowered into these holes are designed never to be recovered. They are precision instruments built for one-way trips. Subglacial ocean access demands something even more ambitious. Instruments that must not only survive the high-pressure, low-temperature environment at the ice base, but must also make real-time measurements and transmit data back through hundreds of meters of ice, water, and cable to a surface station that may itself be drifting on a moving ice sheet. Data transmission through ice is not a trivial problem. Radio waves do not penetrate ice effectively. Acoustic signals propagate, are subject to reflections and interference from the layered structure of the glacier. Fiber optic cables provide the clearest communication pathway, but they are vulnerable to shear forces from ice movement, and their presence means the borehole must remain open, continuously, actively, for as long as data transmission is required. The SALSA project, the Subglacial Antarctic Lake Scientific Access Project, confronted all of these challenges simultaneously when it drilled into Lake Mercer beneath the West Antarctic ice sheet in December 2018. The team used a specialized hot water drill to bore through 1,084 meters of ice in less than 50 hours, then deployed a suite of instruments through the borehole into the lake below. Water samples were collected. Sediment cores were taken from the lake floor. The instruments measured temperature, salinity, and current speed. And crucially, biologists searched the water for signs of life. They found it: crustaceans, fish-like creatures, microbial mats coating the lake sediment. In a body of water isolated from the atmosphere for potentially millions of years, with no sunlight, extreme cold, and crushing pressure, life had not merely survived. It had diversified into something resembling an ecosystem. The discovery shook the scientific community not because it was entirely unexpected. Subglacial Lake Vostok in Antarctica had shown microbial life in the early 2000s, but because of the apparent complexity. These weren't just bacteria clinging to existence. These were multicellular organisms, visible to the naked eye, thriving in conditions that textbook biology would have previously dismissed as incompatible with animal life. But the window that allowed this discovery was brutally narrow. The SALSA team had roughly 60 hours from the moment the borehole reached the lake's surface to the moment it closed. The diameter of the access hole allowed instruments no wider than 25 centimeters. The sterility protocols required to prevent contamination of the isolated ecosystem demanded that every surface, every fluid, every component that entered the borehole had been exposed to UV radiation and filtered to remove biological contaminants. A process so thorough that it added weeks to the pre-deployment preparation timeline. And the entire operation, conducted in the Antarctic summer when temperatures at the surface were still well below freezing, required a field camp that had been airlifted in pieces to a location 640 kilometers from the nearest permanent research station. The North Pole presents all of these challenges simultaneously, and then adds several more that are unique to the Arctic specifically. The Arctic subglacial environment is not simply a colder, higher version of what scientists have accessed in Antarctica. It is geologically distinct, hydrologically more complex, and embedded within a political geography that adds layers of complication that no amount of engineering can solve. The ice above is thinner in places but far more dynamic. The ocean beneath is connected to active circulation systems that interact with Atlantic and Pacific water in ways that Antarctic subglacial lakes, sealed from the global ocean for millions of years, do not. And the scale of the system, measured not in individual lakes, but in an entire ocean basin overlaid by mobile ice, means that point measurements, however heroically obtained, cannot capture the behavior of the whole. Darkness compounds everything. The instruments that descend beneath Arctic glaciers operate in total, absolute darkness, illuminated only by whatever lights the instrument package carries. Light at depth is limited to the instruments themselves and to the bioluminescent organisms that may inhabit the water. Cameras can record, but only what is immediately in front of them, and in water that may carry sediment particles stirred by the drilling process itself, visibility can drop to centimeters. Scientists working in this environment essentially operate blind, relying on sensors and measurements rather than direct visual observation, making inferences from numbers rather than from the direct witness of the world below. This is the geometry of the problem. A dynamic, moving barrier of ice hundreds of meters thick, beneath which lies a high-pressure, lightless, near-freezing environment accessible only through a borehole no wider than a household bucket, open for hours rather than days, in one of the most logistically remote environments on Earth. Add the contamination constraints, the data transmission challenges, the equipment miniaturization demands, and the unpredictable ice dynamics above, and you begin to understand why the subglacial world beneath the Arctic remains, in almost every meaningful sense, uncharted. For most of human history, the idea that liquid water could exist beneath kilometers of ice would have seemed impossible. Ice, by intuitive definition, is where water becomes solid. The freezing point, NT, is 0 degrees Celsius. Below the ice should be more ice, or bedrock, or nothing. But nature, as it so often does, ignored the intuitions of those who hadn't yet done the mathematics. The discovery of subglacial lakes beneath the Antarctic ice sheet began with Soviet aircraft. During the late 1950s and 1960s, Soviet researchers conducting aerial surveys of Antarctica noticed anomalies in their radio echo soundings, a technique that sends radar pulses through ice and measures the return signal from the ice bed interface below. Normally, the return signal from bedrock is diffuse, scattered by the irregular surface of rock and sediment. But in certain regions, the return was flat, bright, and perfectly reflective, the signature of liquid water. The Soviets reported their findings, but the implications were not immediately grasped. It took decades before the glaciological community fully accepted what those readings meant. Beneath the East Antarctic ice sheet, In an area that had been continuously glaciated for at least 15 million years, there was a lake, a large lake. Lake Vostok, named for the Soviet research station above it, is approximately 250 kilometers long and 50 kilometers wide, with a maximum depth of 800 meters. Its surface sits 3,750 meters below the ice sheet above. It has been sealed from the atmosphere for an estimated 15 million years, during which time it has accumulated water from geothermal heating at its base and from the slow melting of overlying ice under the immense pressure. The lake is not static. Currents circulate within it, driven by temperature gradients and the asymmetric melting and refreezing of ice at different points along the roof above. It is, in miniature, a deep ocean system, complete with its own stratification, chemistry, and apparent biosphere. Vostok was the first, but it was not the last, and it was not the largest. As radio echo sounding surveys multiplied across Antarctica throughout the 1990s and 2000s, the map of subglacial lakes grew with astonishing speed. By 2020, more than 400 subglacial lakes had been identified beneath the Antarctic ice sheet alone. Some of these lakes are connected by subglacial rivers, channels of meltwater flowing beneath kilometers of ice, draining from one lake basin to another in response to hydraulic pressure gradients. The subglacial hydrological system of Antarctica is not a collection of isolated puddles. It is a continent-spanning drainage network, hidden beneath one of the most inhospitable environments on the surface of the Earth. The Arctic tells a different story, and the difference matters enormously for understanding why exploration there is so much harder. The Greenland ice sheet, the largest glacial body in the northern hemisphere, sits atop a landmass. Like Antarctica, it has a subglacial hydrological system, and radar surveys conducted by NASA's Operation Icebridge, a multi-year airborne survey using radar-equipped aircraft flying systematic transects over Greenland, have revealed a complex network of channels, lakes, and drainage pathways beneath the ice. Camp Century, a U.S. military base constructed beneath the Greenland ice sheet in the 1960s using tunnels cut into the ice, sat above a bed that science would only later reveal to be riddled with meltwater drainage features. But the Arctic Ocean itself is the truly extraordinary element. The ocean floor beneath the sea ice of the Arctic Basin sits on average about 1,000 meters below the surface, though portions of the basin are far deeper. The Molly Hole north of Svalbard reaches 5,608 meters, making it the Arctic Ocean's deepest point. This seafloor is overlaid, for much of the year and in some areas year-round, by sea ice ranging from newly frozen thin sheets barely centimeters thick to ancient pressure ridges several meters thick. The space between the underside of this sea ice and the ocean below is, in a very real sense, a subglacial environment, one that is in constant motion, constantly evolving, and almost entirely unexplored. The underside of Arctic sea ice is not flat. It is a landscape of pressure ridges, keels, and features that extend downward into the ocean like inverted mountain ranges. These ice keels can reach depths of 40 or even 50 meters below the surface, channeling ocean currents, creating sheltered microenvironments in their lee, and providing attachment surfaces for organisms that have adapted to life in the coldest, darkest reaches of the marine environment. Beneath multi-year ice, entire ecological communities exist. Ice algae that photosynthesize during the brief Arctic summer when light penetrates, amphipods that graze on the algae, Arctic cod that feed on the amphipods, and seals that dive to hunt the cod. The food web of the Arctic Ocean is to a significant degree organized around and dependent on the underside of the ice. That ice is disappearing. The 2012 minimum Arctic sea ice extent, the point in each year's cycle when ice cover reaches its smallest, was approximately 3.41 million square kilometers, roughly half the average minimum extent recorded in the late 1970s when satellite measurements began. By 2023, single-year minimums were consistently among the lowest ever recorded. The oldest, thickest multi-year ice, which once dominated the central Arctic, has declined by more than 90% since 1985. The ecosystem organized around the underside of that ice is losing its structural foundation. And yet, as the ice retreats and makes some parts of the Arctic more accessible to surface observation, the subglacial environments most urgently in need of study, the basal environments of the Greenland ice sheet's outlet glaciers, the grounding zones where glacier ice meets the ocean, become simultaneously more dynamic and more dangerous. The grounding zone, the transition between glacier ice resting on bedrock and ice floating freely on the ocean, is where the most consequential melting occurs. Warm Atlantic water intrudes along the ocean floor, driven by the density difference between salt water and the fresher, colder meltwater produced by the glacier. This Atlantic water contacts the base of the glacier and the grounding line, melting ice from below at rates that can exceed several meters per year. The process is invisible from the surface. It occurs in darkness, under pressure, at the critical junction where the stability of the entire ice sheet is determined. Jakobshavn Isbrae, Helheim Glacier, Kangerlussuaq. These are the great outlet glaciers of Greenland, conduits through which the ice sheet drains into the ocean. They account for a disproportionate share of Greenland's mass loss, which now totals approximately 280 billion tons of ice per year. Understanding how fast they are melting requires knowing what is happening at their grounding zones, the subglacial environment par excellence. And reaching those grounding zones requires threading instruments through fjords clogged with calved icebergs, beneath floating ice tongues, into water near freezing and under pressure, at the very location where the glacier is most actively discharging both ice and meltwater into the ocean. It is, as one glaciologist memorably put it, like trying to take a biopsy from the heart of a patient who is in the middle of cardiac surgery and won't hold still. Chapter 4. What lives in the dark? The creatures found in Lake Mercer were a shock even to the scientists who found them. That microbes could survive in isolated, lightless, cold subglacial environments was established. Lake Vostok's water samples, carefully extracted to avoid contamination, had yielded genetic material consistent with bacterial life. But bacteria are the expected survivors. They have been found in hydrothermal vents, in acidic hot springs, in the cores of nuclear reactors, in the stratosphere. Bacteria are, in the most literal sense, everywhere. Finding them beneath ice is not surprising. It is confirmation. Finding something larger was a different category of discovery entirely. The Salsa team's video footage from the Lake Mercer deployment showed creatures moving through the borehole camera's field of view, small, transparent, with features that suggested crustaceans, identifiable as animals, multicellular, visibly alive, in water that had been cut off from the sunlight-driven food web that underpins virtually all complex animal life on Earth. The question that immediately presented itself was not merely how they had survived, but what they were eating, and what they were eating was eating, and how that entire trophic chain sustained itself in the complete absence of photosynthesis. The answer, as best as science has assembled it, points to chemosynthesis, the process by which certain microbes derive energy not from sunlight but from chemical reactions. In hydrothermal vent systems on the deep ocean floor, chemosynthetic bacteria form the base of food webs that support tube worms, clams, crabs, and fish in complete independence from the sun. The energy source is the chemical disequilibrium between the hot, mineral-rich vent fluids and the surrounding cold seawater. Subglacial environments may support analogous systems, fueled not by hydrothermal heat, but by the weathering reactions between meltwater and bedrock. As glacial meltwater moves through subglacial channels, it dissolves minerals from the rock below, creating chemical gradients that chemosynthetic microbes can exploit. The microbes are the foundation. Everything above them in the food web is built on chemistry rather than sunlight. This has profound implications for astrobiology, the study of life's potential beyond Earth. Europa, one of Jupiter's moons, is believed to harbor a liquid water ocean beneath a shell of ice estimated to be between 10 and 30 kilometers thick. Enceladus, a moon of Saturn, actively erupts water vapor and ice particles into space through geysers fed by a subsurface ocean heated by Theta. L forces. Both of these worlds may have chemistry not entirely unlike the subglacial environments of Earth: cold, dark, pressurized water in contact with rock, potentially with chemical gradients that could support microbial life. The discoveries made in Antarctic subglacial lakes have therefore been watched with intense interest by planetary scientists who see in them a proof of concept. Life can exist in a lightless, isolated, icy subsurface world. The Arctic subglacial environment adds additional complexity to this picture. Unlike the isolated lakes of Antarctica, many of which have been sealed for millions of years, the subglacial environments of the Arctic are connected to each other, to the ocean, and to the surface through seasonal melt cycles. The Greenland ice sheet's base receives meltwater from the surface during summer, when surface temperatures rise above freezing and melt ponds form across the ice sheet's surface. This surface meltwater drains through crevasses and moulins, near vertical shafts in the ice, descending hundreds of meters to the glacier's base, where it enters the subglacial drainage system. The journey takes hours to days. The meltwater carries with it organic material from the surface, pollen, dust, fragments of biological material blown onto the ice from surrounding landscapes. It arrives at the base as a seasonal pulse of both water and nutrients. This connectivity means that the subglacial ecosystem of the Greenland ice sheet is not static and isolated like Vostok or Mercer. It is dynamic, pulsed, seasonally variable, and it connects to the ocean through the glacier's front, where subglacial meltwater emerges at the grounding line, mixing with seawater to create upwelling plumes that draw nutrient-rich deep water toward the surface. These plumes are visible from satellites as anomalies in ocean color, patches of turbulent, nutrient-laden water that attract fish, seabirds, and marine mammals. The food chain of the fjords off Greenland's coast begins, in a significant sense, at the base of the glacier, in the dark, pressurized subglacial environment that humans have barely touched. What exactly lives in the spaces between Greenland's glacier base and its bedrock is almost entirely unknown. The technical challenges of access have prevented systematic biological sampling. Basal ice samples, cores of ice from near the glacier's bed, have yielded microbial genetic material in quantities that suggest active communities, not merely dormant survivors. The sediment beneath the ice, where water has been in contact with bedrock for decades or centuries, may harbor communities structured around the chemical weathering reactions that release minerals from ground-up rock. But the organisms themselves, their identities, their metabolic strategies, their relationships to one another, remain almost entirely uncharacterized. Beneath the Arctic sea ice, in contrast, the biology is somewhat better understood, though still incompletely. The underside of multi-year sea ice hosts communities of ice algae, primarily diatoms, microscopic photosynthetic organisms that live within the brine channels that thread through sea ice like a three-dimensional network of tiny tunnels. These channels can be millimeters wide, their walls made of ice, their interiors filled with water so salty that it remains liquid at temperatures as low as -15 degrees Celsius. The algae that live within them are among the most extreme organisms on Earth, adapted to cold that would instantly freeze most biological membranes, salinity levels that would desiccate most cells, and light levels that fluctuate from the near-total darkness of the polar winter to the continuous illumination of the midnight sun. Arctic cod, Boreageticida, are perhaps the most consequential vertebrates in the Arctic marine ecosystem. They shelter beneath sea ice, feeding on the amphipods and other small crustaceans that in turn graze on ice algae. They breed in winter, when the ice is thickest, spawning in near-freezing water at depths down to 900 meters. Their eggs and larvae drift under the ice for months before reaching maturity. And they are the primary prey of virtually every large predator in the Arctic marine ecosystem: ringed seals, bearded seals, beluga whales, narwhals, polar bears, seabirds. Remove the Arctic cod and the food web above it collapses. Remove the ice algae that feed the Arctic cod and the cod follow. Remove the sea ice itself, and the algae have nothing to grow on. This is the chain of consequence that makes the subglacial environment more than a scientific curiosity. The biological communities structured around the underside of Arctic sea ice represent a foundation that the entire Arctic food web rests upon. They are not peripheral, they are central, and they are changing visibly, measurably, irreversibly in response to the warming that is reducing sea ice extent, thinning multi-year ice, and shifting the T. Ming of the sea ice cycle in ways that decouple biological processes that co-evolved over millions of years. There is a line drawn in the darkness beneath the ice that may be the most consequential geographic feature of the 21st century. Scientists call it the grounding line. It is not a line in any visual sense. No one has ever stood at the grounding line and looked in both directions. It is a transition, a zone where glacier ice in contact with bedrock gives way to glacier ice floating on the ocean. On one side of the grounding line, the ice is anchored, restrained, moving as a coherent mass with friction at its base. On the other side, it floats, no longer in contact with rock, subject to the buoyancy of seawater, and vulnerable to melting from below by ocean heat that the ice sheet's own geometry allows no protection against. The grounding line is where the fate of sea level rise is decided, and humanity cannot see it, cannot reach it, and has or the grounding line retreats. The process is self-amplifying, and without a reversing force, a shallower section of bedrock that could pin the ice in place, or a significant cooling of the ocean, it does not stop. Thwaites Glacier in West Antarctica is the most studied example of marine ice sheet instability in action, but Greenland's outlet glaciers show the same dynamics in an Arctic context. Jakobshavn Isbrae, which drains roughly 6% of the Greenland ice sheet, has a bed that sits hundreds of meters below sea level. Its grounding line has retreated by approximately 40 kilometers since the 1990s. As it retreated, the glacier's flow speed increased from roughly 20 meters per day to more than 40 meters per day, the fastest moving glacier on Earth. The retreat was triggered in large part by the arrival of warm Atlantic water from the Atlantic Ocean that had circulated north, subducted beneath the colder, fresher surface water of the Greenland fjords, and made contact with the glacier's grounding line. The temperature difference between this Atlantic water and the melting point of ice is only a few degrees. But those few degrees, applied to a grounding line zone over years and decades, produced a retreat measured in kilometers. Measuring what is happening at grounding lines requires instruments that can survive in some of the most hostile and inaccessible environments on Earth. CTD instruments, sensors measuring conductivity, temperature, and depth, have been deployed beneath floating ice tongues by threading cables through boreholes drilled from above. Autonomous underwater vehicles have been programmed to navigate beneath ice shelves, mapping the geometry of the ice base and the temperature structure of the water below. Seal-mounted sensors, accelerometers, and CTDs attached to elephant seals and Weddell seals, which regularly dive beneath sea ice, have provided unexpected data sets on the temperature and salinity of water masses under the ice. But none of these approaches can place an instrument at the grounding line itself, in the critical zone where ice contacts the ocean floor and where warm water intrudes to drive melting. The grounding line of a major outlet glacier is not a place where equipment remains stable for long. The ice above is moving, sometimes rapidly. Icebergs calve from the glacier front at irregular intervals, generating waves, ice tsunamis, that propagate beneath the floating ice tongue. The sediment at the grounding line is disturbed by the glacier's motion, by subglacial meltwater emerging at high pressure, and by the turbulent mixing of fresh and salt water that occurs when they meet. Instruments deployed near grounding lines have been lost to calving events, buried by sediment, damaged by ice keels, and simply crushed by the weight of moving ice. The environment demands robustness that pushes against miniaturization requirements, and miniaturization requirements push against robustness. It is an engineering contradiction embedded in geography. The consequences of failure to understand the grounding line are not abstract. The Greenland ice sheet contains enough water to raise global sea levels by approximately 7.4 meters if it melted entirely. The West Antarctic ice sheet, which is ALS, subject to marine ice sheet instability, holds enough additional water to add another 3.3 meters. These are not projections for next year or next century. In their extreme totality, the ice sheets take millennia to fully drain. But the rate of drainage is determined by what happens at the grounding line, right now, in the darkness beneath the ice. And the rate appears to be accelerating. NASA's GRACE satellite mission, which measures gravitational anomalies caused by changes in mass distribution on Earth's surface, detected Greenland losing an average of 280 billion tons of ice per year between 2002 and 2019. The rate of loss in the most recent years of that period was higher than in the earliest years. The trend is not slowing. What is the ocean temperature at Jakobshaven's grounding line today? What is the melt rate per unit area at the contact between Atlantic water and Greenland glacier ice? How far inland has Helheim's grounding line retreated in the last 5 years? These are not questions that climate modelers have answered with the precision that policy makers need to plan coastal infrastructure. They are open empirical questions, solvable in principle with the right instruments in the right places. But getting the right instruments to the right places means penetrating one of the most inaccessible and dangerous environments on Earth. The gap between what we need to know and what we can measure is not primarily a gap of scientific understanding. The physics are well enough understood. The gap is one of access, physical, logistical, engineering access to a place that actively resists being visited. It is the most consequential data gap in climate science, and it sits beneath the ice. The dream of navigating beneath Arctic ice is as old as submarines themselves. Jules Verne sent the Nautilus beneath the polar ice cap in 1870, emerging at the North Pole in a scene that generations of actual naval engineers would spend the following century trying to replicate. The appeal was not merely exploratory romanticism. From a military standpoint, the Arctic Ocean offered something extraordinarily valuable to a submarine commander: continuous cover. An adversary with no satellite, no aircraft, no surface vessel that could locate a submarine operating at depth beneath the ice was effectively blind to that vessel's position, speed, and intentions. The Cold War made the Arctic Ocean the most strategically consequential submarine operating environment on Earth. The USS Nautilus, named, deliberately, for Verne's fictional vessel, became the first submarine to complete a transit beneath the North Pole in August 1958. The passage was achieved not by waiting for a gap in the ice, but by diving deep enough to pass beneath it entirely. Relying on the ship's nuclear propulsion to provide unlimited underwater endurance, and its inertial navigation system to track position in an environment where radio signals from surface-based navigation aids could not penetrate the ice above. The transit took less than 4 days from the Bering Strait to the Atlantic, covering approximately 1,830 kilometers beneath continuous ice cover. Captain William Anderson surfaced to broadcast a laconic message: Nautilus 90 north. The mission was complete. But Nautilus was not exploring the underside of the ice. It was transiting beneath it, at depths where the ice keels above posed no obstacle to a vessel operating at several hundred feet depth. The ice ceiling far above was a navigational hazard, a hard boundary that prevented emergency surfacing, but not an object of study. The first submarine mission, actually designed to examine what lay beneath the ice, was different in intent and considerably more dangerous in execution. The scientific value of submarine observations beneath Arctic ice was first seriously exploited by the U.S. Navy's scientific programs during the Cold War, when classified submarine cruises conducted oceanographic measurements as a secondary mission to their primary military purpose. The data collected on these cruises, water temperature and salinity profiles, acoustic measurements, ice thickness measurements using upward-looking sonar, were largely classified until the early 1990s, when portions were declassified and released to the scientific community. The release caused a minor revolution in Arctic oceanography. Measurements showing the subsurface temperature and salinity structure of the Arctic Ocean basin over decades revealed trends that surface observations had missed entirely. The progressive warming and deepening of the Atlantic water layer that circulates beneath the cold, fresh surface water of the Arctic. Declassification revealed something else: the extraordinary difficulty of operating any vessel beneath sea ice. Submarines navigating the Arctic faced not only the tactical problem of avoiding ice keels that could reach 30 meters below the surface, but also the navigational challenge of operating in an environment where conventional magnetic compasses become unreliable near the magnetic pole. GPS signals cannot penetrate water or ice, and acoustic positioning systems are subject to anomalous propagation through layered water masses with sharply different densities. The environment was hostile to the technologies that submarines relied on, and the consequences of navigational error in a region where emergency surfacing through thick ice might be impossible were severe. The development of autonomous underwater vehicles, AUVs, offered a potential solution to the access problem that submarines could not fully resolve. AUVs are torpedo-shaped robots, typically between 2 and 6 meters long, capable of navigating underwater without a tether by following pre-programmed mission profiles or responding to sensor inputs in real time. Unlike remotely operated vehicles, ROVs, which are connected to surface ships by cables, AUVs operate independently, departing from a ship, conducting their mission, and returning to a pre-planned recovery point. The absence of a tether eliminates the risk of the cable snagging on ice features and allows the vehicle to navigate in areas inaccessible to surface vessels. The challenge of operating AUVs beneath Arctic sea ice is fundamentally different from operating them in open ocean. In open water, an AUV that fails to return to its recovery point can be tracked acoustically, its position approximately determined, and a recovery operation mounted. Beneath sea ice, the surface is inaccessible to the recovery vessel. Acoustic signals are reflected and scattered by the irregular ice base, and the vehicle's own navigation system may accumulate errors over a long mission that make its final position uncertain. If an AUV runs low on battery or suffers a fault beneath solid sea ice and cannot return to the deployment point, it is lost. No surface ship can come to its location. No diver can recover it. It sinks or drifts with the current beneath the ice until it can eventually be found, if the ice retreats far enough to allow access, or not at all. Several AUVs have been lost beneath Arctic ice, and their loss has not been trivial. These are instruments worth several $million, carrying irreplaceable scientific sensors and batteries charged with whatever limited data they managed to collect before their systems failed. The loss of the Otto Sub-3 AUV beneath Pine Island Glacier's ice shelf in Antarctica in 2005, during a mission to measure melt rates at the glacier's grounding zone, was a defining moment for subglacial AUV operations. The vehicle, which had been designed and built over years and had already completed successful under-ice missions, failed to return from a dive beneath the floating ice shelf. Its final position was never determined. The data it collected in its last mission, potentially critical measurements of the melt rate at one of the world's most important grounding zones, vanished with it. The development of AUVs capable of reliably operating beneath sea ice has since become one of the priority engineering challenges in polar oceanography. The Otto Sub Long Range, a successor system designed specifically for extended under-ice operations, incorporates redundant navigation systems, including ice avoidance sonar that maps the ice base in real time to prevent collisions with ice keels. It uses a buoyancy engine rather than propellers for vertical motion, reducing power consumption and extending mission endurance to days rather than hours. It communicates acoustically with an acoustic modem system that can relay data through the water column to surface buoys deployed at openings in the ice. And it carries a contingency behavior. If the vehicle detects that it cannot return to its planned recovery point, it navigates to a calculated open water area based on its knowledge of the ice cover at mission start, then surfaces and deploys an emergency beacon. Gliders, a variant of AUV that moves through the water by alternately increasing and decreasing its buoyancy, converting vertical motion into horizontal travel through the use of small wings, have shown particular promise for long-duration under-ice missions. Unlike propeller-driven AUVs, gliders carry no rotating machinery and generate virtually no acoustic noise, making them ideal for biological observations that would be disturbed by mechanical vibrations. They move slowly, typically less than 1 meter per second, but they can operate for weeks to months on battery power, making measurements continuously along their sawtooth trajectories through the water column. Gliders have been deployed beneath the sea ice of the Labrador Sea, the Beaufort Sea, and the waters around Svalbard, returning data on temperature, salinity, and biological optical signals that would otherwise require constant ship presence to collect. But gliders, like all AUVs, cannot enter the truly confined subglacial space beneath a glacier's ice base. Their navigation systems require acoustic communication with surface transceivers that cannot be deployed through solid ice. Their recovery requires access to open water or ice camps that may not exist in the target area. And their science payloads, though increasingly sophisticated, cannot yet approach the complexity of the sensor suites deployed through boreholes by research teams willing to invest weeks of drilling effort for hours of in situ access. The machines that have come closest to penetrating the truly inaccessible subglacial environment are cryobots, instruments specifically designed to melt their way through ice, descending autonomously by liquefying the ice directly ahead of them with a heated nose cone. The concept is elegant. A cylindrical robot pointed at one end generates enough heat to melt ice at its tip and descends through the resulting water-filled borehole under gravity, refreeze closing the shaft above it, carrying a tether or fiber optic cable that transmits data back to the surface. Cryobots eliminate the borehole closure problem entirely. They don't need the hole to stay open because they make their own passage. The Ice Mole, developed by a consortium of European universities with funding partly inspired by the interest in exploring Europa, has demonstrated the cryobot concept in both laboratory and field settings, melting through ice at the Athabasca Glacier in Canada and the blood-red subglacial lake beneath Antarctica's Taylor Glacier. The device can navigate through ice by heating specific segments of its body differentially to alter its direction, avoiding obstacles while descending. It has reached subglacial environments and returned samples. In principle, it could descend through hundreds of meters of Arctic ice to reach the base. In practice, cryobots face their own set of severe limitations. Their descent speed is limited by the thermal power available and the thermal properties of the ice, typically measured in meters per hour rather than per day, meaning that penetrating 500 meters of ice requires many hours of continuous operation. Their tether grows longer with each meter descended, adding weight and the risk of tangling. And perhaps most critically, once a cryobot has descended to its target depth, returning it to the surface is extraordinarily difficult. Ice has refrozen above it, and the vehicle must either melt its way back up, which requires energy it may not have, or be abandoned in place with only the tether for data transmission. Most cryobot designs are conceived as one-way instruments. The glaciers of the Arctic are not merely barriers to the world below. They are archives. Within their layered ice, compressed over hundreds of thousands of years, lies the most complete record of Earth's atmospheric and climatic history that humans have yet accessed. Understanding what the ice remembers and developing the techniques to read that memory has been one of the most consequential scientific endeavors of the 20th and 21st centuries. And the act of reading the record requires the same borehole access technologies that subglacial exploration demands, creating an unexpected unity between the quest to understand climate history and the quest to understand what lies beneath. Ice cores are extracted from glaciers using drilling systems that remove a continuous cylinder of ice from the surface downward, section by section, preserving the layered structure that records each year's snowfall as a discrete band. In the summer-winter cycle, snow that falls in summer is transformed by sunlight and slightly warmer temperatures into a coarser, less reflective layer, while winter snow is finer and more reflective. These alternating bands are visible in ice cores from the past several thousand years, providing an annual record, a tree ring chronology translated into ice. Deeper in the core, where pressure has compressed millennia of snowfall into ice that has forgotten its annual layering, other proxies take over. Isotopic ratios of oxygen and hydrogen atoms, which record the temperature of the atmosphere when the snow fell. Concentrations of trace gases trapped in air bubbles, which preserve a direct sample of the ancient atmosphere. Accumulations of volcanic ash, which date the core to known eruptions, and concentrations of rare isotopes produced by cosmic ray bombardment of the upper atmosphere, which vary with the activity of the sun. The Greenland ice cores, GISP2, GRIP, North GRIP, NEAM, collectively extend the Arctic climate record back approximately 130,000 years, to the last interglacial period when global temperatures were several degrees warmer than today, and sea levels were 5 to 9 meters higher. The Antarctic cores, Vostok, EPICA Dome C, extend the record beyond 800,000 years, through 8 full cycles of glaciation and interglacial warming. The records they contain have transformed the science of paleoclimatology, providing empirical constraints on climate sensitivity. How much warming results from a given change in atmospheric greenhouse gas concentrations that no computer model alone could supply? Reading these records requires reaching them. The deepest portions of the Greenland ice cores, the ice that preserves the climate of 130,000 years ago, sit more than 3,000 meters below the ice surface, at temperatures of approximately degrees Celsius, under pressures comparable to those at significant ocean depth. Drilling to these depths takes years. The EPICA Dome C ice core in Antarctica, which holds the longest unbroken ice core record in the world at 3,270 meters, required 6 years of drilling between 1999 and 2004. Every meter required careful management of the drilling fluid, a synthetic liquid injected into the borehole to prevent its walls from collapsing under the pressure of the surrounding ice, the temperature of the drill head, and the recovery of the core from the drill without fracturing the fragile ancient ice. At the very bottom of a deep ice core, in the few hundred meters immediately above the glacier's base, the ice behaves differently from the clean, layered archives above. Basal ice is disrupted, folded, sheared, mixed by the glacier's internal dynamics. It contains rock particles entrained from the bed, pockets of liquid water, and biological material washed in from the subglacial environment. It is simultaneously the most intriguing and the least interpretable part of the core. The annual layering that provides a clock for the upper ice is destroyed. The climate signals are overprinted by the effects of glacial flow, and the biological material, the DNA, cell fragments, and organic compounds derived from the subglacial ecosystem, is mixed and diluted in ways that make it difficult to determine what lived there and when. The search for older ice that predates the 800,000-year record of the Antarctic deep cores and could potentially extend the climate archive to 1 million years or beyond, is a driving force behind current ice core research. In the oldest glacial cycles, buried deeper in the ice sheets of both Antarctica and Greenland, scientists expect to find a shift in the dominant periodicity of ice ages, from a 41,000-year cycle driven by changes in Earth's axial tilt to the 100,000-year cycle that has dominated the past 800,000 years. The cause of this shift, known as the mid-Pleistocene transition, remains one of paleoclimatology's central open questions. Resolving it requires ice more than 1 million years old, which means drilling deeper than any ice core has yet reached, into ice that has been subjected to the most extreme conditions of flow and deformation, and which sits very close to or at the glacier's base. Several sites in East Antarctica are currently candidates for this oldest ice drilling, identified through radar mapping of the ice thickness and modeling of ice flow that suggests ancient ice may be preserved at depth without being destroyed by basal melting or disrupted by deformation. The Antarctic Ice Core Project, coordinated by an international consortium, is in the process of identifying the optimal drill site. The same radar surveys used to locate old ice also reveal the subglacial topography below, the mountains, valleys, and lake basins that underlie the East Antarctic ice sheet. The search for old ice and the exploration of the subglacial environment are, in this sense, the same expedition undertaken with the same tools. In the Arctic, the Greenland ice cores have already told a story that has dramatically reshaped understanding of climate stability. The Dansgaardischer events, rapid climate oscillations discovered in the Greenland ice core, record by Danish physicist Willy Dansgaard and Swiss scientist Hans Easter in the 1980s, show that the climate of the North Atlantic region can shift dramatically in extraordinarily short periods. During the last ice age, temperatures over Greenland warmed by as much as 10 to 15 degrees Celsius within decades. In some cases, the available evidence suggests within years. These events, which recurred approximately 25 times between 70,000 and 12,000 years ago, are thought to be driven by shifts in the Atlantic meridional overturning circulation, the system of ocean currents that moves warm water from the tropics toward the North Atlantic and cold water back toward the equator. When this circulation weakens or collapses, the North Atlantic cools dramatically. When it resumes, warming follows within years. The ice sheet itself is a player in this drama, not merely a recorder of it. The freshwater discharged from melting ice changes the density of surface waters in the North Atlantic, potentially disrupting the thermohaline circulation that drives the AMOC. Events known as Heinrich events, periodic massive discharges of icebergs from North American ice sheets into the North Atlantic during the last ice age, are recorded in deep-sea sediment cores as layers of ice-rafted debris, and correspond in time to cooling events in the Greenland ice core record. The mechanism linking ice sheet behavior, freshwater discharge, and ocean circulation is exactly the kind of feedback that climate scientists most urgently need to understand. And it operates at the grounding line in the subglacial environment, precisely where observation is hardest. In August 2007, two Russian mini-submarines descended 4,200 meters to the floor of the Arctic Ocean directly beneath the North Pole and planted a titanium Russian flag in the seafloor sediment. The gesture was theatrical. The flag has no legal standing whatsoever under international maritime law, but the intent behind it was entirely serious. Russia was asserting a claim that the Lomonosov Ridge, an undersea mountain range that extends from Russia across the Arctic Ocean, is an extension of the Russian continental shelf, and that the resources beneath the ocean floor along its length therefore belong to Russia under the United Nations Convention on the Law of the Sea. The underwater planting of a flag at the North Pole encapsulated a geopolitical reality that constrains subglacial exploration as much as any engineering challenge. The Arctic Ocean is surrounded by 5 coastal states: Russia, Canada, the United States, Norway, and Denmark, through Greenland, each of which has exclusive economic rights over the ocean resources within 200 nautical miles of its coast. But the Arctic Ocean is small enough, and the bordering states' claims extensive enough, that there is significant overlap in the central basin and significant geological complexity in determining where one nation's continental shelf ends and another's begins. Scientific research in the Arctic Ocean is therefore not simply a matter of pointing a ship toward the North Pole and beginning to drill. Research in the territorial waters of any Arctic state requires that state's permission. Research in the claimed but disputed zones requires navigating a legal landscape that has not yet been resolved by any international tribunal. The Lomonosov Ridge claim, advanced not only by Russia, but also by Denmark and Canada, who contend that the ridge is an extension of their own continental shelves, has been the subject of competing submissions to the UN Commission on the Limits of the Continental Shelf since the early 2000s. The Commission's determinations are technical and non-binding. They determine only whether a submission meets the geological criteria for an extended continental shelf, not whose claim takes precedence when 2 states claim the same territory. Beneath the ice, the politics become more complicated rather than simpler. The Mosaic expedition, which locked the German research icebreaker Polarstern in Arctic sea ice in October 2019 for a full year of drifting observation, required extensive diplomatic preparation to conduct research in waters through which the ship drifted at the whim of ice and current, crossing through the claimed zones of multiple Arctic states without any ability to predict in advance exactly where the ice would carry it. Scientific research vessels working in the Central Arctic often drift across jurisdictional boundaries that on paper require permits that, in practice, no one knows how to issue for a vessel whose location is determined by nature rather than by the ship's captain. Russia's relationship with Arctic science has oscillated between cooperation and obstruction over the decades since the end of the Cold War. Soviet-era data collected during decades of drifting ice stations, research camps established on multi-year ice flows and allowed to drift across the Arctic basin, were shared with Western scientists after declassification in the 1990s and proved invaluable for understanding the basin's hydrography and ice dynamics. But Russia's invasion of Ukraine in 2022 effectively ended direct scientific cooperation between Russian and Western Arctic researchers, closing off access to Russian territorial waters and ending collaborative programs that had operated for decades. Several key monitoring stations, including those that tracked sea ice extent and ocean temperature in the Russian Arctic, went dark or became inaccessible to international researchers. The data gap created by that political rupture is not small. Canada's relationship with Arctic sovereignty is, if anything, more complex. Canada claims the Northwest Passage, the shipping route through the Arctic archipelago north of the Canadian mainland, as internal Canadian waters, a position not accepted by the United States or most other maritime nations, who regard it as an international strait. The dispute has practical consequences for scientific research. Vessels operating in the passage, with instruments deployed in the water, require Canadian permits that the Canadian government has at times declined to issue expeditiously. The same archipelago that overlies portions of the Arctic Ocean most dramatically affected by climate change, is subject to a sovereignty dispute that generates bureaucratic friction in the path of scientific expeditions. Beneath all of this lies a question that geopolitics has only partially engaged with. Who is responsible for monitoring, studying, and ultimately protecting the subglacial environment beneath the ice of the high Arctic? The Arctic Council, an intergovernmental forum including the 8 Arctic states plus observer states and indigenous peoples organizations, has provided a framework for scientific cooperation and environmental protection in the Arctic. Its working groups have produced assessments of Arctic climate change that are among the most comprehensive available. But the Arctic Council has no enforcement mechanism, no treaty-based mandate, and its consensus-based decision-making has been effectively paralyzed since 2022 by the diplomatic rupture between Russia and the other 7 members. The consequence is a monitoring gap at the very moment when the Arctic is changing most rapidly. The rate of Arctic warming, roughly 4 times the global average, a phenomenon known as Arctic amplification, means that the environment being studied is transforming faster than the institutional frameworks for studying it can adapt. Ice that has persisted for decades is disappearing within years. Glaciers are retreating at rates that would have been considered catastrophic a generation ago. And the data needed to understand these changes, to model their trajectories, and to anticipate their consequences for sea level, ocean circulation, and global weather patterns sits beneath ice that no one has fully legal, logistical, or technical permission to explore. Most people, when they think about melting ice, imagine the surface. They picture glaciers retreating uphill, their termini shrinking year by year, calving faces collapsing into the sea in dramatic events that make footage for news broadcasts. They imagine melt ponds forming on Greenland's surface in summer, brilliant blue against white ice, draining into crevasses and disappearing. They think of warming air temperatures, of summer days that are slightly too warm for the ice to survive. This is the visible melting, the kind that satellites can see and cameras can record. It is not the most consequential melting, not by a considerable margin. The melting that matters most happens in the dark, at the base of glaciers, at grounding lines hundreds of meters below sea level, where warm ocean water contacts ice that has never known sunlight. This basal melting produces no dramatic calving events, no surface lakes, no footage that a television documentary can use. It produces, instead, a slow thinning of the ice from below, an invisible excavation that proceeds at rates of meters per year, and that fundamentally changes the mechanical behavior of the ice above. When ice is thinned at its base at a grounding line, the grounding line retreats. When the grounding line retreats onto deeper bed topography, the rate of ice discharge into the ocean increases. When ice discharge increases, sea level rises. The causality is clean and inescapable, and the critical step, the ocean heat reaching the grounding line, is almost entirely unmonitored. The mechanism by which warm water reaches glacier grounding lines in the Arctic was not well understood until the 1990s, and its quantitative importance was not fully appreciated until the 2000s. The Arctic Ocean is stratified in a way that might intuitively seem to protect the ice. The surface layer is cold and fresh, derived from river runoff, precipitation, and melting sea ice, and it floats above a warmer, saltier, denser layer that originates in the Atlantic. This warmer Atlantic layer, with temperatures ranging from 1 to 3 degrees Celsius above freezing, sits at depths of 200 to 900 meters in much of the Arctic Ocean. Above it, the cold freshwater cap insulates the surface, preventing direct exchange. The ice that forms at the surface is therefore insulated from the warmth below by the very physical properties that distinguish fresh water from salt water. In the open Arctic Ocean, this stratification largely holds, but in the fjords of Greenland, the deep, glacier-carved channels that connect the ice sheet's edge to the ocean, the stratification breaks down in ways that allow the warm Atlantic water to reach the glacier's front. The fjords are narrow and deep, some exceeding 1,000 meters in depth. The Atlantic water, circulating in the North Atlantic and mixing its way northward, subducts beneath the lighter surface waters and intrudes along the fjord floors. At the innermost end of the fjord, where the glacier terminates, this warm water contacts the ice face at depths that may reach several hundred meters. It melts the ice from below and from the sides, undermining the submerged ice face that makes up the majority of the glacier's terminus, and the meltwater produced, cold, fresh, buoyant, rises as a plume, drawing more warm Atlantic water inward behind it. The quantification of how much this ocean melting contributes to Greenland's mass loss has required a combination of remote sensing, oceanographic measurement, and modeling that has taken decades to assemble. Studies published in the late 2010s and early 2020s, using data from oceanographic surveys conducted in Greenland's fjords, suggest that submarine melt at glacier termini contributes significantly to the total mass loss from those glaciers. In some cases, The submarine melt rate is comparable to or exceeds the calving rate, making it the primary mechanism of mass loss. This was a significant revision of earlier models, which had attributed most Greenland mass loss to surface melting and dynamic calving driven by ice flow. The practical implication is severe. If submarine melting at glacier termini is as important as the data suggests, then the trajectory of Greenland's ice loss is determined not only by air temperature trends, which are relatively well monitored and modeled, but by the temperature and circulation of the Atlantic water that reaches the fjord floors. That circulation is itself subject to change. The AMOC, the overturning circulation that brings warm Atlantic water northward, is showing signs of weakening. A weaker AMOC might deliver less warm water to Greenland's fjords, potentially reducing submarine melt, or the temperature of the water being delivered might increase even as the volume decreases. The interactions are complex, the data sparse, and the models uncertain. The uncertainty matters because sea level rise projections used for coastal planning and policy making depend critically on assumptions about the rate of ice loss from the Greenland and Antarctic ice sheets. The IPCC's sixth assessment report in 2021 projected global sea level rise of 0.32 to 0.62 meters by 2100 under intermediate emissions scenarios, with an upper-end estimate exceeding 1 meter. But these projections explicitly acknowledged deep uncertainty around the contribution of ice sheet dynamics, the term used for the kind of dynamic mass loss driven by submarine melting and grounding line retreat that occurs in the subglacial environment. The report identified the ice sheets as the dominant source of uncertainty in sea level projections, and the dominant source of that uncertainty as the behavior of the grounding line, precisely the feature that humanity cannot see, reach, or monitor effectively. The cities that will be affected by this uncertainty are among the most populated on Earth. Bangkok sits approximately 1.5 meters above current sea level. Miami's airport runway elevation is less than 3 meters. Dhaka, the capital of Bangladesh and home to over 20 million people, averages about 8 meters above sea level, but has extensive low-lying areas far closer to sea level. Jakarta, whose 10 million inhabitants already experience regular flooding, has been sinking for decades due to groundwater extraction, bringing sea level effectively closer to the surface even without climate change. For all of these cities, the difference between 40 centimeters of sea level rise by 2100 and 1 meter of sea level rise represents a difference measured in infrastructure investment, in displacement, in survival. And that difference is being determined right now, at grounding lines beneath Arctic and Antarctic ice, in complete darkness. There is a species of amphipod, a small shrimp-like crustacean, called Gammarus wilkitskii, that lives almost its entire life within the brine channels of Arctic multi-year sea ice. It is among the most ice-specialized organisms on Earth, adapted over millions of years to the specific physical and chemical properties of ice that has persisted for multiple winters. Its pore channels, its salinity, its temperature, its biological community of algae and bacteria. Gammarus wilkitskiae does not live at the surface of the sea ice or beneath it. It lives within the ice itself, threading its way through the three-dimensional network of brine channels that permeates the ice like a circulatory system. The channels are its habitat, its food source, its breeding ground, and its protection from predators. Multi-year ice. The ancient, thick ice that was once the dominant ice type in the Central Arctic has declined by more than 90% since satellite observations began in 1985. The ice that Gammarus wilkitskiae requires for its specialized life history is disappearing. The brine channels of first-year ice, which forms each winter and melts each summer, have different physical properties. They are larger, less stable, and support a different and less diverse community of organisms. The highly specialized adaptations that Gammarus wilkitskiae has accumulated over millions of years of evolution in multi-year ice are becoming liabilities in a world where multi-year ice no longer dominates the Central Arctic. The fate of Gammarus wilkitskiae is a microcosm of what is happening throughout the subglacial and underice ecosystem of the Arctic. The biological communities that depend on the specific properties of ice, its thickness, its age, its chemical composition, its microstructure, are being squeezed by a changing environment that is evolving faster than evolution can track. But the ecological consequences of this loss are only partially understood, because the organisms and communities affected are largely inaccessible to direct observation. We know Gammarus wilkitskiae is declining because researchers have compared the records of specimens collected decades ago with contemporary surveys. But those surveys are themselves sparse, because collecting organisms from within sea ice requires ice camps, drilling, careful extraction of brine channel contents, and taxonomic expertise that is concentrated in a small number of research groups worldwide. The microbes within subglacial lakes and at glacier bases represent an even more acute case. The microbial communities beneath the Greenland ice sheet have been sampled at precisely a handful of locations, drill sites where boreholes reached the glacier bed, where basal ice was carefully extracted for microbiological analysis. The communities found at each of these sites are distinct, suggesting that the subglacial environment is not homogeneous, but rather a patchwork of different habitats, some dominated by bacteria that derive energy from iron reduction, others by bacteria that oxidize hydrogen produced by the reaction of water with rock minerals, others by communities apparently fueled by ancient organic carbon stored in the overridden sediments beneath the glacier. Each of these communities represents a distinct evolutionary lineage, adapted over long timescales to a specific set of chemical and physical conditions. Most of these communities have never been observed. The vast majority of the glacier bed beneath Greenland, hundreds of thousands of square kilometers, has not been reached by a single borehole. The organisms that live there have not been collected, cultured, or even detected by the genetic probes that can identify organisms without culturing them. They may include novel bacterial lineages, entirely new metabolic strategies, enzymes adapted to function at extreme cold and pressure that could have applications in biotechnology, industrial chemistry, or medicine. Or they may be relatively unremarkable extensions of microbial communities found elsewhere in cold, dark, pressurized environments. Without access, the question cannot be answered either way. The race to characterize these communities before the glaciers that shelter them retreat and disappear is a genuine scientific urgency. Unlike the organisms of a rainforest, whose loss is tragic but whose habitats persist in some form even under disturbance, the organisms of the subglacial environment will lose their habitat entirely when the ice retreats. The subglacial lakes will drain. The brine channels will melt. The cold, pressurized, lightless spaces that provided the selective pressures driving millions of years of evolution will simply cease to exist. The organisms adapted to them will not migrate. They will go extinct. And the scientific record of their existence will be limited to whatever samples can be collected before the ice disappears. The timeline for this loss is not distant. The Greenland ice sheet is losing mass at an accelerating rate. The outlet glaciers that drain it are retreating into narrower fjords, their grounding lines moving inland year by year. Some of the smaller ice caps on Iceland and Svalbard have already lost sufficient volume that they no longer qualify as glaciers by scientific definition. The Ökürkut Glacier in Iceland, once a feature substantial enough to appear on maps, was officially declared dead in 2014. In 2019, a group of scientists, Icelandic officials, and local community members held a funeral for it, marking the first glacier in Iceland to be formally recognized as lost to climate change. The memorial plaque they installed on the exposed bedrock reads in Icelandic and English, "A letter to the future." It notes the glacier's ice mass, its year of death, and the atmospheric carbon dioxide concentration at the time, 415 parts per million. It closes with a note of accountability. "We know what is happening and what needs to be done. Only you know if we did it." What that plaque does not mention, could not mention, is the community of organisms that lived beneath Ökürkut throughout its existence. The microbes in its basal ice, the communities at its bed, the organisms that spent their entire lives in an environment now exposed to air and sunlight for the first time since the glacier formed. They were never sampled, never cataloged, never even confirmed to exist. They are gone without record, without observation, and without name. The engineers and scientists who have spent careers trying to access subglacial environments are not without ideas. The frustration of the field is not one of imagination, but of resources and development time. The gap between what researchers know would be needed and what has been built, tested, and deployed remains wide, and bridging it requires sustained investment on timescales that compete awkwardly with grant cycles of 3 to 5 years. But the concepts exist. Some are in advanced development. Some are being tested in analogous environments. And the convergence of several technological trends, robotics, materials science, computing power, and autonomous navigation, suggests that the next decade may see the deployment of instruments capable of genuinely exploring the subglacial world in ways that current technology cannot. Miniaturized cryobots represent one of the most promising paths. The limiting factor in current cryobot designs is the power required to melt through ice at usable speed. a trade-off between the thermal energy available, the size of the borehole created, and the rate of descent. The ice mole and similar vehicles melt boreholes large enough to pass through them, which requires significant power. But instruments that do not need to pass through the borehole, instruments that are the borehole, melting their way to depth and operating in place rather than deploying through a larger hole, can be made smaller, requiring less power for each meter of progress. A cryobot 10 centimeters in diameter, designed to carry a minimal but targeted sensor suite, temperature, salinity, pressure, and a simple camera, could potentially be produced and deployed in sufficient numbers to provide coverage across multiple subglacial access points. The key enabling technology is not the melting itself, but the power supply. A cryobot operating for hundreds of hours requires either an energy-dense battery system or a cable to a surface power source, and both carry their own challenges. Nuclear power sources, specifically the kind of radioisotope thermoelectric generators that have powered space probes from Voyager to Cassini, have been proposed as the power source for deep ice penetrators. RTGs convert the heat produced by radioactive decay into electricity, requiring no moving parts and no fuel supply. They operate continuously for decades. A cryobot powered by an RTG would have, in principle, unlimited endurance, able to melt through any thickness of ice and operate at depth for years rather than hours. The proposal has been advanced most seriously in the context of Europa mission concepts. A spacecraft carrying a cryobot landing on Europa's icy surface, the cryobot melting its way through several kilometers of ice to reach the ocean below. The same technology would be applicable to Arctic glaciers, and the thickness of ice to be penetrated is far less than what a Europa mission would face. The obstacle to deploying RTGs in polar field settings is not engineering. It is regulatory and political. Radioisotope power sources require radioactive material, which triggers treaty obligations, export controls, environmental permitting requirements, and public concern that no amount of scientific justification can easily overcome. The regulatory pathway to deploying an RTG in Greenland or on Arctic Sea ice would take years to navigate even if the technology were ready today. It is, in the language of policy, a non-starter for the near term. Less exotic power solutions are more immediately tractable. High-energy density batteries, whose development has been driven primarily by the electric vehicle industry, have improved dramatically in the past decade and continue to improve. Lithium-sulfur batteries, currently in advanced development, promise energy densities more than twice those of current lithium-ion systems. For a cryobot of fixed volume, doubling energy density doubles the range. The amount of ice it can penetrate before its power is exhausted. The same commercial pressures that drive automotive battery development are inadvertently advancing the enabling technology for subglacial exploration. Swarm robotics, the deployment of large numbers of small, simple robots that collectively accomplish tasks no single robot could manage, offers another approach to the coverage problem. rather than attempting to build one large, complex, expensive vehicle capable of surveying a significant portion of the subglacial environment. Swarm approaches would deploy many small, cheap vehicles, each capable of basic sensing and communication, whose collective coverage creates a picture of the whole. The challenge in a subglacial context is communication. Individual vehicles in the swarm must relay data to their neighbors and ultimately to the surface, and navigation in a featureless, dark, pressurized environment where conventional GPS and radio do not function. Acoustic communication through water can serve as the swarm's nervous system, but the geometry of a narrow borehole or subglacial channel limits the range and bandwidth of acoustic links. Sensing technology is advancing independently of vehicle design. Environmental DNA, eDNA, analysis can detect the presence of organisms in a water sample by identifying the genetic material they shed into their environment, without requiring the organisms themselves to be captured or even observed directly. A small water pump and filter system deployed through a borehole can collect eDNA samples from the subglacial environment, which are then analyzed in a surface laboratory using sequencing technology that can identify organisms present at concentrations of cells per milliliter. The eDNA approach has already been applied to subglacial lake water from Antarctic drilling projects, providing the most comprehensive microbial census yet achieved from these environments. Applied systematically across multiple borehole sites in Greenland or the Arctic, eDNA sampling could produce a biological map of the subglacial ecosystem at a fraction of the cost and technical complexity of deploying sophisticated in situ biological sensors. The satellites that observe the Arctic from above are also becoming more capable in ways relevant to subglacial science. Cryosat-2, operated by the European Space Agency, uses radar altimetry to measure the surface elevation of ice sheets with centimeter-scale precision, detecting the subtle deflation of the ice surface that occurs when subglacial lakes drain or when grounding line retreat accelerates ice discharge. GRACE-FO, successor to the GRACE satellite mission, measures gravitational anomalies caused by mass redistribution on Earth's surface, tracking the month-to-month changes in ice sheet mass that result from the integrated effect of surface melt, ice discharge, and basal melting. Ice-penetrating radar, operated from aircraft by NASA and ESA, maps the thickness and base topography of ice sheets across their full extent. None of these systems can directly observe what is happening at the glacier base, but they constrain the behavior of the subglacial system from above, providing the macro-scale context within which the in situ measurements made through boreholes must be interpreted. The integration of these data streams, satellite, airborne, in situ, into coherent models of subglacial behavior is itself an emerging field. Ice sheet models that incorporate realistic representations of basal hydrology, grounding line dynamics, and ocean ice interactions are becoming more sophisticated as computing power grows, and as the fundamental physics of these processes is better understood. The models, in turn, identify the specific subglacial processes and locations that most drive uncertainty in sea level projections, telling field scientists where the next borehole should go, what measurements it should make, and what the model will do with those measurements. The loop between observation and modeling, when it works well, is the engine of scientific progress. In subglacial science, the loop is only beginning to close. There is a thought experiment worth sitting with. Imagine that the Greenland ice sheet became transparent overnight, that scientists could look down through the ice as if through glass and see the bed below in its entirety. The subglacial channels and lakes, the warm water intruding at grounding lines, the microbial communities living in basal sediment, the geometry of the bed, all of it visible. What would change? The answer is almost everything we're trying to figure out about the future of sea level rise. The uncertainties in ice sheet models are not primarily in the physics of ice flow or ocean circulation. Those equations are well constrained by laboratory measurements and theoretical derivation. The uncertainties are in the boundary conditions, the topography of the bed, which determines where water accumulates and how ice flows, the thermal state of the base, which determines whether basal sliding occurs, the subglacial hydrology, which lubricates the ice bed interface and modulates flow, and the ocean temperature at grounding lines, which drives the submarine melt that is pulling the ice sheet from beneath. If the ice were transparent, if humanity could see these boundary conditions directly, the models would immediately become more accurate. The range of plausible sea level rise projections would narrow. The planning horizon for coastal adaptation would lengthen. The ice is not transparent, and the alternative instruments deployed through boreholes, beneath submarines, on the backs of seals, under gliders, at the end of fiber optic cables lowered through holes that close in hours, is not fully adequate. The sampling density achievable with current technology, even in the best funded and most ambitiously executed field campaigns, leaves vast regions of the subglacial environment entirely uncharacterized. Every point measurement is surrounded by a vast space of unknown conditions, extrapolated by models whose assumptions may not hold. This is not a counsel of despair. Science proceeds through exactly this kind of incremental, imperfect observation. Each measurement, however sparse, constraining the space of possible realities, each new instrument design expanding the reach of human knowledge into environments that previously admitted no observation at all. The history of subglacial exploration is short, and it is a history of astonishing progress. 30 years ago, the existence of subglacial lakes was a speculation based on anomalous radar returns. Today, more than 400 have been mapped in Antarctica alone. Several have been directly accessed and sampled, and the microbial life within them has been partially characterized. 30 years ago, no AUV had ever operated beneath sea ice. Today, dozens of vehicles conduct under-ice missions routinely, and the data they return constrains ocean models that would otherwise be blind to the Arctic's subsurface. But the pace of discovery is in a race with the pace of change. The subglacial environment that scientists are slowly, heroically beginning to access is simultaneously the environment that drives the changes threatening to alter coastlines worldwide. The tools needed to win this race, better cryobots, more capable AUVs, expanded borehole programs, sustained international cooperation, require investment and institutional commitment that the geopolitical landscape of the 2020s does not obviously provide. The Arctic Council's paralysis, the interruption of Russian Western scientific cooperation, the chronic underfunding of polar research relative to the stakes involved, these are not engineering problems. They are political ones, and they may prove harder to solve than any borehole closure. There is something profound in the particular nature of the barrier between humanity and the subglacial world. It is not distance. The environments in question are measured in hundreds of meters, not light years. It is not danger of the most acute kind. People have survived at the poles, on the ice, in submarines beneath the ice, for centuries. It is the combination of cold, pressure, darkness, dynamic ice, sterility requirements, logistical remoteness, and political complexity, each individually manageable and together constituting a barrier that has so far resisted comprehensive penetration. The ice does not have intentions. It does not choose to hide, but it hides nonetheless, and what it hides may be the most consequential information that the 21st century needs to find. The last unexplored regions of Earth are not exotic-sounding places in the deep tropics or the far ocean trenches. They are beneath ice that covers 10% of the planet's surface and holds 70% of its fresh water. They are beneath the North Pole, beneath the glaciers of Greenland, beneath the sea ice that is disappearing from the Arctic at a rate that will make this window of subglacial exploration shorter rather than longer. The irony of climate change and subglacial science is precise and cruel. The warming that is making some portions of the Arctic more accessible to surface observation is simultaneously accelerating the changes at the glacier base that make those changes most urgent to understand, while increasing the dynamism and instability of the ice above in ways that make borehole access more difficult, more dangerous, and more time-constrained than before. The scientists who dedicate careers to this work understand the stakes in a way that is difficult to convey to those who have not watched a borehole close, have not lost an AUV beneath ice, have not collected water samples from a lake sealed for millions of years in the hours before the access shaft refroze around their equipment. They work in a place where the ordinary assumptions of field science, that the environment will wait for you, that a missed observation can be made up next season, that the data will eventually come, do not hold. The ice will not wait. It is moving now, melting now, changing the world now, in darkness that no satellite can pierce and no camera has yet entered. The question of whether humanity will understand what is happening beneath the Arctic's glaciers before those glaciers reshape the world's coastlines is not rhetorical. It is an empirical question, answerable in principle, with a deadline that is measured in decades rather than centuries. The tools to answer it exist, in prototype or in concept. The science to use those tools has been developed, painstakingly, over generations of polar research. What remains is the commitment, institutional, financial, political, to deploy those tools with the urgency that the timeline demands. Beneath the ice, the world is being remade, slowly, invisibly, without witness. The only question worth asking now is whether humanity will find a way to watch before it is too late. 8 to do anything, but adapt to what it has already set in motion.